Okay, so let's look at the other two ways that we can transfer heat. Instead of doing it by conduction with direct contact, we can use this process called convection. Convection is essentially transferring the energy by having the atoms move from one place to another before they release that energy. And there's a very simple principle, and that is that hot atoms rise and cool atoms descend. And the reason why they do that is because they change their density. As you heat an object, it expands, it becomes less dense, and therefore it begins to float. If you cool an object, it condenses, it becomes smaller, takes up less space, therefore becomes more dense, and therefore sinks compared to the surrounding material. Whether this is hot water or cold water, or hot air or cold air, the principle is the same. This only works in fluids. Okay, and fluids means liquids or gases. Okay, solids cannot undergo the process of convection unless we turn them into a liquid or a gas. So this works pretty simply. So if I heat up water, what I end up with is the hot water rises, and as it reaches the top, it releases some of that heat in terms of conduction and the second form of energy that we're going to look at. And so then it becomes cooler. It falls over to the side. The material here is pushed off to the side, and then the cooler material begins to sink. The cooler material pushes the material that was previously here over towards the center, and we end up with something that are called convection cells. So here I've shown two convection cells. Convection cell is simply the rolling over of the water or the liquid or the fluid, depending on what we're looking at. This could be air. On the Earth we see vast convection cells where air rises, moves over to a different location on the Earth, and then descends. And so convection cells are a way of transferring the energy by having the atoms down here collect up the energy, move up to a new place, and then release the energy. And this again cannot be done in a solid substance. Our last way for transferring energy is through photons of light. And a photon of light is simply a little packet, like an individual packet of light. We think of light in terms of its wave properties oftentimes, but light actually does come in little packets, little individual portions, and that's where the term photons comes from. So in this case, the one thing about photons of light is that this is the only form of energy transfer that can it can occur in a vacuum. Now the sun has all kinds of temperature changes going on, temperature transfers going on inside of it. There's conduction, there's convection, there's radiation. But once the heat reaches the surface of the sun, there's only one way to get it from the surface of the sun to the surface of the earth, and that is through radiation. It cannot be passed from the sun to the earth through conduction or convection, but only through radiation, and that's because radiation is capable of traveling not only through atoms, but radiation can travel through the vacuum of space. So a really important aspect that makes radiation very different from the other two forms. Radiation does not require atoms, and conduction and convection require atoms for that transfer to occur. Now, this brings us to a simple equation, and that is the amount of energy that is leaving an object. We would typically express it in terms of the power. We would say how many joules per second are leaving that object, and it turns out, sorry, I shouldn't say equals to. We're not going to look at the exact equation, but we are going to look at some of the variables that it depends on. So we would say it is proportional to, and it turns out to be proportional to two main properties. It's proportional to the area, right? So that should make sense. I mean, the more area that you have to radiate your energy, the faster that you're going to radiate it, the more power that you're losing. So a very small object at the same temperature will not be radiating as much energy away as a larger object would at the same temperature. The larger object with larger surface area releases more energy. And so, for example, if a star had a bigger area than the sun, a bigger surface area, it would be radiating more energy. The star would appear brighter because it's releasing more energy per second than the sun is. A smaller star would release less energy per second, and therefore it would look dimmer. We wouldn't see as much light coming from it. Now that should be pretty understandable. The more area you have, the more energy that you can release, because all of the energy has to be released at the surface. And again, we're talking about radiation. The temperature relationship is a little bit different, though. The power released by the object goes as the fourth power of the temperature. Now that's a very unusual relationship. I don't think we've ever seen something that went as the fourth power of an object. So it sets up some pretty interesting things, and this, of course, T is in Kelvin, absolute temperature. You definitely have got to use the absolute temperature here. We're not talking about a temperature change. We're talking about the actual temperature of the object. And that's an important point. When we look at temperature changes, it doesn't matter whether we use Kelvin or Celsius, but when we want the power equation, or we want the energy that's in an object, then we have to use the Kelvin scale. So, for example, how does the power change if the temperature doubles? Well, let's take a look. So let's look at the new power. Well, sorry, I keep writing equals. Shouldn't write equals. Not the power equals. The power is proportional to A times, now I have 2t to the fourth. So I need to take the fourth power of 2. So that's 2 times 2 is 4, times 2 is 8, times 2 is 16. So P prime is proportional to 16A t to the fourth. Now here's my original number. The power went up by 16 times. Doubling the temperature causes you to release 16 times more energy than you would have released back at the original temperature. So you can see that when you take something to the fourth power, the small change in the temperature has a tremendous change in the amount of radiation that's leaving this object, whereas doubling the surface area only has a doubling effect. Double this, this doubles. Double this, 16 times increase.